Good day, dear colleagues. Let me present a report dedicated to Apache Match adaptive image and video watermarking schemes on handheld mobile devices. Mobile devices provide a huge amount of multimedia information sending to the members of social groups every day. Sometimes it is required to authorize the sending information using the limited computational resources of smartphones, tablets, and laptops. The hardest problem is with smartphones, which have the limited daily energy and battery life. This report includes some issues of texture and motion analysis adopted for mobile watermarking techniques. We consider two variants of watermarking schemes for still image and short videos. Also, we shall report the obtained experimental results and make conclusions. There are two scenarios for using mobile watermarking techniques. The first scenario is to implement the embedding and extraction schemes using proxy servers. In this case, the watermarking scheme does not differ from conventional techniques, including the advanced ones based on adaptive paradigms, deep learning, multi-level protection, and so on. The main issue is to hide the embedding and extracting information from the proxy server. The second scenario is to provide a pseudo-optimized algorithm with respect to robustness, interceivability, and capacity using limited mobile resources. We developed the second approach as a light version of adaptive image and video watermarking schemes. We propose a simple approach for creating a patch-based set for watermark embedding using texture estimates in still images and texture motions estimates in frames that are highly likely to be iframes in MPEG notation. We embed one or more watermarks using relevant large-sized patches according to two main criteria: high texturing in still images and high texturing or non-significant motion in videos. Limited memory and significant battery consumption are the main challenges of watermark embedding and extraction using the mentioned above devices. Conflicting constraints prevent the expectation of outstanding results. As well known, the robustness, imperceivability, and capacity are the main criteria of watermarking process. At the time, the computational costs is addition criterion for mobile device. Another challenge connects with infinite number of possible attacks. The complete taxonomy of attacks is presented here. Note that each type of attack can be done with different unknown parameters, and a known combination of several types attacks can be applied. At present, there is no universal watermarking algorithm robust to the most types of attacks. As a rule, various watermarking schemes are more likely robust to the limited types of attacks. In order to enhance the imperceivability and the robustness for grayscale histogram-based image features as DC, skewness, kurtosis, and entropy were chosen as input data for designing association rules based on the a priori algorithm. As a result, the ratios of imperceivability, robustness, and embedding rate with low execution time were obtained. This CNN-based scheme consists of preprocessing network for both host image and watermark, a watermark embedded network, and attack simulation for training, and a watermark extraction network to extract watermark whenever necessary. It has three peculiarities. The first is the host image resolution adaptability. This is to apply the proposed method to any resolution of the host image. The second peculiarity is the adaptability of the watermark information. This is to provide usability of any user-defined watermark data. The last peculiarity is the controllability of the trade-off relationship between watermark and visibility and robustness against attacks. In the study, page-based correspondence were chosen as more robust and reliable, but time-consuming approach regarding the pixel-based approach. The original page match algorithm estimates dense approximate nearest neighbor correspondences between patches of two image regions. The generalized patch match correspondence algorithm was enhanced in three ways. First is to find nearest neighbors, to search the patches across scales, rotation translations, and to match the patches using arbitrary descriptors and distance. The patch match algorithm is successfully used as an approximate nearest neighbor algorithm on top of the learning descriptors after using Siam's CNN for optical flow computational. There are three ways to decrease the computational complexity of BMA. The first way involves using a fixed pattern. The three-step search is a simple and efficient three-step search. The four-step search and the diamond search are algorithmically considered as fastest, but they cannot match the dynamic motion content. Second way is reducing the search points. This category includes the adaptive route pattern search, the fast block matching using prediction, the block-based gradient descent search, and the neighborhood elimination algorithm. These methods assume that the error function behaves monotonically and evaluates slow movement. Decreasing the computational overhead for every search point is a third way. The matching cost is replaced by a partial or simplified version under assumption that all pixels within each block move by the same finite distance. Such algorithms are able to avoid local minima, predicting the search center closer to the global minimum. However, the enhanced predictive zonal search and hexagons algorithm cannot correctly detect motion of very small objects. And the last way is use evolutionary approaches such as lightweight genetic block matching, the genetic four-step search, and the particle swarm optimization block matching. However, the evolutionary approach are characterized by large computational time, which is not ideal for mobile devices. The texture classification, texture segmentation, and texture synthesis and texture shape are the main issues of texture analysis in spatial domain. Our task is close to texture segmentation under criterion of high texturing. We can enforce texture segmentation by silence analysis, removing regions which attract human attention. General method of texture analysis are usually classified into four categories: statistical, structural, model-based, and transform-based methods. Statistical methods are based on the moments of distribution functions of pixel intensities. Calculation of statistical moments is one of the simplest approach to evaluate the texture features. Some of them are presented on the slide. To estimate a degree of high texturing, we use three measures of homogeneity, smoothness, and entropy. Another possible approach is to estimate a degree of high texturing using the local binary patterns, LBP. They provide a technique of a unique encoding of central pixel with position regarding to its local pixel neighborhood using a predefined radius value. In the study, we compare the results of texture estimation based on moments and LBP in terms of smartphone performance. Images received from the cameras of modern smartphones are high resolution, while the screen resolution is not so high. We also use different block size to choose optimal of them. The original patch match algorithm is based on non-parametric patch sampling methods. The initial procedure fills the nearest neighborhood field with either random offsets or prior information. The iterative update procedure propagates good patch offsets to adjacent pixels and then randomly searches the best offset in the neighborhood. We adapt the original patch match algorithm, exploiting the idea that the initial random procedure can be replaced by directed search based on a coarse interframe difference. Also, we can suppose that the adjustment patches are cooperatively shifted in a part of the frame. It is recommended to use the Halton criteria as a fixed number of iterations, no more than 4 or 5 iterations. In such manner, we form a set of frames with small interframe differences, exclude all detected movement patches from each frame of this set, and create a motionless map for this set. A hypothesis is that one of such frames will be iframe, which then used to embed the watermark embedding. In the case of an image watermarking scheme, we only apply texture analysis, selecting highly textured regions. For video watermarking scheme, spatio-temporal analysis should be utilized, since a video sequence is compressed by unknown types of codec when transmitted through unprotected channels. We need to detect a set of frames, one of them will be iframe. To do this, we detect scene changes, which are excluded from a watermarking process, but after that a set of iframes can be detected. Second, we apply motion and texture analysis for these frames. This process are clarified in figures. Bottom is figures for images, and top is the example of selecting the relevant regions for video. We tested several hundred of images and dozens of videos received from smartphones, cameras, first by selecting the relevant regions and second by embedding watermarks in the form of small images or short text messages. Experiments show that adaptive watermarking schemes provide better robustness and invisibility than conventional watermarking schemes. The experiments were conducted using several datasets. First is the Click 2019 professional dataset, which contains high-quality images, including complex textures and foreground objects, which allows us to evaluate the loss of quality when embedding watermark. Second is the dataset named after Felice Polana, watermarked or non-watermarked images, includes data for training the algorithm with different types of watermarks. Most images contain different levels of ink and vary in quality and resolution. We also used high-quality video sequences obtained from the drone videos dataset, characterized by complex camera movement and natural textures. Examples of such images are depicted in a figure from all three datasets. The process of region selecting example for embedding a watermark is presented on the slides. Top images are regional, then we detect texture by entropy and using patch-based masks with different pixel size, patch size. And the bottom frame are regions selected for embedding a watermark. The quality of the watermarked images was estimated by well-known peak signal to noise ratio, or PCNR, and mean square error, MSE, metrics where we compare a watermarked and original frame. As higher PCNR are, as better than image. Depending on the size of the image, we can get a big difference in the amount of the embedded information. The amount of such information is tens of kilobytes for an HDTV format and increases with an increase of the block size. This is due to the fact that the block motion estimation algorithm becomes less sensitive to small objects and objects with complex texture and contour structure. This is not a disadvantage for embedding the watermark and practically does not lead to a degradation of image quality. Example of image quality and PCNR metric for some of the images are presented on the slides in the table. The paper proposes an algorithm for embedding a watermark for handheld mobile devices. The main idea is to improve the speed of embedding using faster methods. We evaluate the relevant regions for embedding a watermark based on texture and motion estimators and exclude foreground objects or visible objects closer to the center of the frame. This allows us to improve the quality of watermarked images and avoid embedding a watermark in those areas of the frame that can be attacked and distorted when transferring data over unprotected channels. Evaluation of the efficiency of the algorithm on existing databases shows high speed and robustness to distortion, regardless of the complexity of the image. The experimental results confirm the robustness of our approach with minimal computational costs. Thank you for attention.